During the course of the war, we have developed many different radar sets, each built to do one certain job better than anything else. However, regardless of size, design, or job, all pulsed radar sets operate on the same basic principles, and the component parts of all these sets are essentially the same. And whichever set you work on, your job, the repairman's job, is the same: to keep your set working and working right all the time. That goes for every set, from the latest searchlight set, the ANTPL, to this early settler, the SCR-268, on alert in the theater of operations. This one's in Italy. But what's about to happen to it can happen anywhere, on any set, and often does. The operator is on target. Whoa there, wait a minute, what goes on here? Now that's better. Hey! That does it. Well, what is it? Set trouble? Jamming? Mice in the local oscillator? Whatever it is, it's got to be fixed in nothing flat. Bombers won't wait. And it's your job. It's you radar repairmen who will be handed the problem and the nothing flat to do it in. So you have to know your stuff. You have to know if it's set trouble or not. And if it is, locate it and fix it. In the first film of this series, we reduced all radar sets into a simplified block diagram. You saw how the timer originates the pulses, the transmitter converts them into RF energy, and the antenna flings them into space. At the same time, remember, the timer sends part of each energy pulse to the indicator, where it starts the sweep of the baseline. The main pip at the beginning of the baseline is formed when part of the energy leaving the transmitter is picked up by the sensitive receiver. The baseline is synchronized with the outgoing pulse and provides us with an accurate electronic yardstick for measuring the distance traveled by each pulse. When a target comes within range, echo signals are reflected. These signals are picked up by the receiving antenna, amplified by the receiver, and finally register on the baseline of the indicator as a target pip. The position of the target pip on the baseline is calibrated by the set, and in that way you find the range of the target. Each set transmits high-frequency radio energy in the form of short pulses, followed by a listening period, one long enough to permit a target echo to return from maximum range. In that way, echo signals can be seen clearly by themselves. To make sure that the proper time intervals are maintained, and that at these intervals each unit is triggered off to a time accuracy of 1/1,000,000th of a second, every set is equipped with a master timepiece called a timer, or sometimes synchronizer or keyer. Here's what the timer of a typical long-range early warning set, the SCR-271D, looks like. And here's its heart, the vacuum tube in the timing oscillator. All the tubes won't look like this, but they all do the same job. Here's what it is. First, it generates a sine wave, where each cycle is identical with all the others. If the sine wave's frequency is 1,000 cycles a second, we have actually divided 1 second into 1,000 equal parts. But in this sine wave, it's impossible to tell where each thousandth of a second begins and ends. That's why it's changed into this, a peaked wave, which can be measured from positive peak to positive peak. This wave is the basic controlling wave of the set. All the component actions of our radar are synchronized with these peaks. For instance, it's part of this peaked wave voltage that passes from the timer to the indicator to trigger off the baseline. This synchronizes the baseline with the outgoing pulse, because at the same time, the same peaked wave triggers a pulse-forming circuit, which creates a new waveform, pulses with flat tops. Notice that throughout these changes, the exact subdivisions of our second in time have not been lost. We still have precisely the same number of positive peaks per second that our original sine wave did. But here is the important difference. In the original sine wave, the voltage rises and falls gradually. The action is easy, never sudden. When we use the rectangular trigger pulse, the voltage rises from 0 to its peak value instantly, remains at that point for the length of the pulse duration, then immediately returns to 0. Pulse duration is also called pulse width. This action of the trigger pulse causes sudden, powerful bursts of energy to be generated and transmitted. Then, with equal suddenness, the energy is turned off while the outbound pulse travels through space. This transmission of radio energy may last from half a microsecond to several microseconds, then goes off for several thousand microseconds. On again, off again. So many pulses per second. Some sets transmit wider pulses than others. These are frequently the early warning sets, which pick up targets as far away as 150 miles. The echoes from the long-range target register on the baseline as a distinct pip. But as the target comes closer to the set, the echo pip on the baseline approaches and may even merge with the main bang and be lost. The long-range sets don't worry about this. They turn the target over to short-range sets. But to track short-range targets effectively, we must keep the target pip from merging with the main bang. That's why short-range sets must transmit narrow pulses or pulses of short duration. With this type of pulse, the set will get a distinct and separate echo pip on the baseline, even at extremely short ranges. We can conclude, therefore, that the width of the pulse largely determines the effective minimum range of the set. Now let's examine the time interval between these pulses. This time interval, or listening period, must cover the time it takes for an outgoing pulse to reach a target at maximum range and return. For a set designed to operate at a maximum range of 20 miles, the timer might generate as many as 4,500 pulses per second. But if the desired maximum range is 100 miles, the listening period has to be longer. And the timer might have time to generate no more than 900 pulses per second. You can see then that one of the basic factors in determining the maximum range of the set is this fixed rate of pulse repetition. It's known as the pulse recurrence frequency, or PRF. To sum up, the timer first generates a sine wave voltage of the proper frequency, changes it to a peaked wave that synchronizes all circuits of a radar system, then causes the shaping of a rectangular wave that triggers the transmitter. The width of each pulse, or the pulse duration, primarily establishes a set's minimum range. While the number of pulses it transmits per second, the pulse recurrence frequency, or PRF, largely determines the maximum range. Timers, remember, control both pulse width and PRF. They vary greatly in size and construction. In this light portable search set, the ANTPS-1, the unit that does the timing is comparatively small. But this long-range early warning set uses a timer that includes a whole rack of complicated equipment. Airborne radar sets, naturally, must be more compact. For example, this B-17 has a radar, the AN-APQ-13, whose timer takes up very little elbow room down there on the bottom shelf. Still, it does the same job that the timer in a large ground station does. Once the timer has generated a voltage wave and it's been shaped into the desired rectangular pulse, the transmitter is ready to take over. It uses the voltage energy received from the timer to trigger off a radio frequency oscillator, which may be one or more high-powered tubes. This is the most important unit in the transmitter. It is here that the set generates powerful pulses of RF energy, which are flung into space by the antenna. This oscillator tube handles extremely high voltages and requires a strong source of energy to make it function. The voltage pulse as it now stands, although it's the right shape, isn't strong enough to trigger the oscillator tube. So the transmitter uses a driver and a modulator to amplify the voltage it receives. In the driver, the pulse is reproduced and amplified. The pulse is further amplified by the modulator. Now it's ready to trigger the RF energy that will be transmitted. In other words, it acts as a switch for the RF oscillator. When this oscillator tube is triggered by the amplified voltage pulse, it oscillates at a very high frequency, hundreds of megacycles per second, for the length of time of the pulse duration. The period when the tube is not oscillating is a listening period. Its length depends on the PRF established by the timer. This PRF also determines the exact microsecond when the tube will again begin to oscillate. As in the case of the timer, the transmitter size varies according to use. Here's one belonging to a large land-based early warning set. Here's an anti-aircraft gun-laying set, the SCR-584, and its transmitter. Here's the compact transmitter of an airborne set, the APQ-13 in the B-17. Whatever the size or shape of the transmitter, the job it does is essentially the same, amplifying the voltage pulse until it's strong enough to trigger the oscillator. The oscillator then generates RF energy. Once the high-frequency radio pulses leave the transmitter, they are carried by a system of transmission lines to the antenna. There are many types of transmission lines: parallel two-wire conductors, coaxial lines, waveguides, and many arrangements. But their purpose is the same: to carry the RF energy from transmitter to antenna with the least possible loss. The more energy that radiates from the lines, the less there will be to radiate from the antenna where it's wanted. When properly timed RF pulses pass through the transmission lines and reach the antenna, they're ready for active duty. The simplest radar systems contain two separate antenna arrays, one for transmitting pulses and one for receiving echoes. For example, on the SCR-527, a GCI set, here's the receiving antenna. Over here's the transmitting antenna. On the 268, the antennas are on the same mount. All antennas operate alike fundamentally. They concentrate radio frequency energy into a narrow beam and radiate this beam in a given direction out into space. A pulse goes out. Say, wait a minute. Before you go hunting targets, suppose you show us just what part of the antenna you came from. That's right. Each of those dipoles radiates energy, and the combination of all dipoles acting together results in a very powerful pulse concentrated into a narrow beam. Some antennas have more dipoles than others, depending on the type of beam desired. The length of the dipole in each set will depend on the wavelength of the RF energy being transmitted. Now let's see how a single one of these dipoles transmits energy. When RF energy is fed to a dipole, it radiates from all sides in the shape of a donut. But since we want the energy to go in a particular direction, we use a reflector, which causes most of the energy to be radiated in one direction. The reflector can be a rod, like the slightly longer one there at the left, tuned to its dipole. Or it can be an untuned wire screen or mesh. Through proper spacing of the dipoles and reflectors, the set focuses the outbound energy into a beam, which, like a narrow beam of light, has its greatest intensity of radiation at the center. Although some radar systems employ two separate antenna arrays, one for sending and one for receiving, most of the newer models use the single antenna system, combining the two functions of sending and receiving. Single antennas are easier to handle and more practical. One type of single antenna employs a parabolic reflector, like the reflector in an automobile headlight. A dipole is located at the focal point of the dish, and a reflector is usually fixed about 1/4 wavelength in front of it. The reflector causes almost all the forward energy from the dipole to be reflected back into the dish. It is then concentrated by the parabola and radiated out in the form of a narrow beam. The returning energy is caught by the dish and focused back to the dipole, now acting as a receiving antenna. An example of this single parabolic type is the antenna of the AN-TPS-3, a portable early warning set, with the dipole on the left at the focal point of the dish, and the reflector a 1/4 wavelength in front of it. The gun-laying 584 also uses a single antenna for both transmitting and receiving. So does the SCR-720, the Aircraft Interception, or AI set, in the night-fighting Black Widow. Underneath this dome in the nose of the ship, the dish scans the area slowly or rapidly, whatever the radar operator desires. Although this single antenna system is obviously more compact, it poses a brand new problem in electronics. That problem is a switch that will enable one antenna to alternate from transmitting to receiving, as often as 5,000 times a second. This switch is called a transmit-receive, or TR switch. It's a combination of spark gaps and transmission lines tuned by stubs to present an easy path for RF energy in one direction, a hard path in another. One spark gap is located in a stub of the transmission line between the transmitter and the antenna. The other is in the stub of the line between antenna and receiver. The system is normally tuned to block off the line from the transmitter and leave the line open to the receiver, like this. The strong RF pulse from the transmitter causes the gaps to spark, changing the values of the tuning stubs, making the path from transmitter to antenna the easy one, and at the same time blocking the path from transmitter to receiver. After the transmitter fires and shuts down, the gaps stop sparking, and the path from antenna to receiver is again open. Now, when the echo returns, the normal action of the lines sends all the energy to the receiver. Once the echo signal returns, it must be picked up and amplified by a suitable receiver. Basically, a radar receiver is the same as the average radio receiver. Both are superheterodynes. The parts and even circuits are a good deal alike. If you understand radio, you'll find the mechanics of the radar receiver pretty easy to grasp. In some sets, when the weak signal enters the receiver, it's amplified immediately. But in all cases, its high frequency has to be lowered before we can work with it any further. It gets lowered in the mixer. Another frequency, generated in the local oscillator, is mixed with it, and the result is a lower intermediate frequency, or IF signal. But this has to be amplified still further. It may go through as many as 7 stages of IF amplification before being fed into the detector. The detector filters out the intermediate frequency, and what's left is like the square pulse that originally triggered the transmitter. But this isn't strong enough yet to register on the indicator, so a final buildup takes place in the video amplifier. The signal is now ready for the indicator. We'll take up the whole subject of indicators in the next film of this series. What you've seen and heard today is a very simple explanation of the different components of any radar set. An illustration of what takes place inside a timer, transmitter, and antenna when they send a pulse of RF energy into space. and in the antenna, receiver, and indicator when the weak returning echo is picked up. In a single second, this cycle of interconnected actions can occur 5,000 times. So you see, the simplest radar is still a complicated piece of equipment. That's why you've got to know what makes each unit tick.